here's what it says. It says when you plug in a negative, you don't get the same thing as the original function. Like you don't get the same thing like here. What you get is the opposite. Okay? So let's see if I can explain this visually. See the big difference here? This one didn't have a minus, this one does, right? Let's do that same example. What if I did -2 here, and I told you that it was at 3? So when I plug -2 into the function, I get 3. But that needs to be equal to the opposite of the function's value at 2. So at 2, what should the value of the function be? -3. See, if at -2 you're equal to 3, then at +2 you should be the opposite, -3. Let's do it again. Let's say at -3, I'm over here at 1. Where would I be at +3? -1 down here.
So would a linear line that's negative be an odd function because if it crosses the origin?
If it crosses the origin, yes. As long as it goes through the origin. Very good. Let me do another point. Let's say at -1 we were here. At +1 I would be that same distance, right? But down. So I'd be here. At 0, well 0 is 0, right? Negative 0 is same as +0. Do y'all see it? If I connect this, we've got, this is not this symmetry, right? It's not y-axis symmetry. It's not x-axis symmetry. It's the origin symmetry. This is the double symmetry, right? It's if I reflect this over, right? If I reflect it, it would do this. That's y-axis. And now flip over the x-axis and you're going to land right on top of yourself. So all odd functions are origin symmetry. Okay?
It's like it's even on the left because every single point has 2, or every single x has 2, or not x, every single y has 2 x's, except for 0.
Yeah, it has to do with the fact that all even functions that have even powers like x squared, x to the 4th, x to the 6th, all even power functions are even. Do this, and all odd, like x cubed, x is a line, right? Y equals x is a line. That's an odd power. Odd is going to give you this. Okay, you got the idea of even and odd visually? Okay, so what we're going to do now is we're going to take a look at an example, maybe. So this just tells you right here what I just said. The theorem, okay, graphs that are even or symmetric to the y-axis, and then the other ones with respect to the origin. Okay. For each of these three, we are going to decide whether or not they are even, odd. Oh wait, do functions have to be even or odd? Like, are there only 2 options? No, there's a third option, which is neither. All right? A function can be even, it can be odd, or it can be neither. So for these 3 graphs, we're going to look at them, and we're going to answer the question, is it an even function, an odd function, or neither? Okay, what type of symmetry do you see on the first one? Y-axis symmetry. Y-axis symmetry means even. Yeah, this is a little tricky. Well, do y'all agree it's not this, right? Like, if we just flip it over the y-axis. Let me flip it over the y-axis. Let me see if I can do that. It would look like this. That's me flipping this piece over, right? And then if this piece comes over, it would look like this. So that's just flipping over the y-axis. If I now reflect that over the x-axis, I'm not going to land. What's going to happen? This part right here now becomes this. I hope that makes sense. The green is reflection over the y, and then the red is the reflection of the green over the x. And that definitely doesn't land on top of itself, does it? And so we have no symmetry here, right? So even, and here we would say neither. And what about this one? Odd. That's odd. Because, again, if you do a double reflection, let me just take this section, reflect it over y, right? And then let me take this over the y. I get that, right? And now reflect that over x. So if I reflect this piece up, it lands right on top of that. And if I reflect that piece down, it lands on top. So this would be odd. This is neither. This is even. Let's see. I don't know what to do about that.
Just move the mouse over.
You think that'll do it?
Yeah.
Let's see.
Probably inactive.
I don't know because, no, that doesn't do it. It's because I'm directly plugged into the HDMI, so I'll do this instead. I'll just unplug it, and then I'll plug it back in. And I'll lose everything. It did not like that. Okay, not energy saving. Would you like to keep the energy saving countdown? Keep it on? Not this session.
It liked that a lot less.
Oh, wait, hold on. Whatever. I already explained my frustration about this building. I think in the beginning of the semester, you know, you build this brand new building with all this taxpayer money, right? And then you don't ask the faculty what they want. All I want in here is a board that would have gone up and been big enough for this projector and wide enough that I could walk from side to side. That's all I wanted. No one asked me. No one asked any of us in the math department. So now we've got all these boards. We said we need more board space. So they put all these boards in the back. Well, what use is that to me here, right? All right, sorry, I'm bitching. Okay, can we continue? Even odd, you got it? Visually? Most students can handle the even odd idea visually, but how about algebraically? So what we're going to look at now are some functions where we don't have the pictures, and we have to determine whether or not they're even or odd just by looking at the functions. So I'm going to put it way up there, but I'll do the work on the board. All right, so is this an even function? Even, odd, or neither. So part A, f of x is x squared minus 5. So the question is this even, odd, neither? How do you spell neither? N-E-I? So that does not follow the I before E except after C, right? Rule that I learned when I was in school. That's the exception.
English is wonky.
Yeah, I know it is. All right, so choose which one. Well, to do this, you could just say, oh, look, it has an even power, but you'd be kind of risking it there. You need to check the property. All right, so let's check even first. So is it even? Question mark. So is f of negative x equal to f of x? That's what it means for something to be even. Right? That's what it means to be even. Is that when I plug in a negative, I get the same as plugging in a positive. Right? That's the definition. Now, I have to figure out, is this true or not, right? So I'm going to do this. Let's do the right side first. What is f of x? It's just that function, right? X squared minus 5. What is f of negative x? We'll plug negative in here for x instead. And you would get negative x squared minus 5. Do y'all see the difference? This is just f of x. This is what you get when you plug negative x into that function. But when I square negative x, what's negative x times negative x? X squared, right? The negative is going to go away. So you're just going to get x squared minus 5. And does that equal x squared minus 5? Yes. Therefore, this is an even function. And we can stop. A function cannot be both even and odd. It's one or the other or neither. Yes, even. Do y'all understand I'm done? I don't need to check odd? Do you have a question?
Yeah, what about like when we did 13, it was like all of them, like X, Y, and origin.
Okay, so when it comes to even and odd, even is y-axis symmetry, odd is origin symmetry, right? When we're looking at pictures, we talk about 3 different kinds. But when you talk about even and odd, we're only looking at 2 different kinds. Does that make sense?
Yeah.
Okay.
If it supplies both the y-axis and origin symmetry, I think it would be because origin generally means odd, and then y is even. But if the function qualifies for both, we would just test both for even and odd. Just test each.
We had this example here, right?
Yeah.
And I think this is what you're saying. This was both even and odd? I'm sorry. That this was all 3 symmetries?
Yeah.
I agree. But this is not a function.
Okay.
Why is this not a function? The vertical line test? Okay, so it is possible to have a relation that has all the symmetries, but when we talk about functions, it's either going to be even, odd, or neither. Good question. Let's look at the next one. So pay attention to this one. Same questions. Is this even, odd, or neither? What does your instinct tell you? Odd, because you see x cubed, but we have to show it. So the first thing I'm going to ask myself is this even? Is this even? Right? Question mark. So I'm going to say, is f of negative x equal to f of x? Question. I don't know, right? The right-hand side of this is just the original function. The left-hand side is what I get when I plug negative x into the original function. Very much like we just did here, right? Now, when you take a negative x and you cube it, negative x times negative x times negative x, are you going to get a positive or a negative? Negative, right? So this turns into, let me just write it here, doing negative x times negative x times negative x, which is the same as negative 1 times negative 1 times negative 1 times x times x times x. Right? There's 3 negative 1s here being multiplied, and there's 3 x's being multiplied. The 3 negative 1s become negative 1, and the 3 x's become x cubed. In other words, I can get rid of the parentheses around this and just turn it into negative x cubed minus 1. Does that equal this? Are those the same? No, those aren't the same. Is it even? No, so it's not even. That does not force it to be odd. You now have to check to see if it's odd. All right? So now I ask, so this right here, not even, right? Is it even? No. Okay, is it odd? Is it odd? Well, what do I need to say? Is f of negative x equal to negative f of x? That's the definition of odd. It means that when you plug in a negative, you don't get the original function, you get a negative in front of the original function. Right? Okay, so do we know what this left-hand side is? We're asking ourselves, do we know what this left-hand side is? We just did that, right, in the previous? So we know that that's what? Negative x cubed minus 1, right? And the question is that equal to the original function, right? The original function, but a negative in front of it. What happens if we put a negative in front of the original function? Let me do it right here. Here's a negative. Here's the original function. That negative must pass through both, right? So the left-hand side is this. We're asking ourselves, is that equal to what? Negative x cubed plus 1. Are they the same? No, they're not the same. They're not the same, right? These are the same, but this is minus 1, that's plus 1. That's not the same. So is it odd? No. So it is neither. Neither, neither, however you want to say it. Okay?
Is there ever a quick way to see if it's even?
Algebraically,
Yeah.
other than if you just like look at it, you've done enough of them, you can tell. No, you have to do the algebraic check. So if you take a step back, what you're doing at the end of the day to check even and odd is you're really looking at f of negative x, right? And you're seeing, first of all, is it equal to the original function? If not, you're saying, is that f of negative x equal to the opposite of the original function? That means change all the signs of the original function. If that's true, if either of those are true, you're going to have even or odd, respectively. Okay, let's see. We need to do another one. How about this one here? 5x cubed minus x. No, wait, 5x cubed. Yeah, 5x cubed minus x. So we're going to take the function, I think it's h of x, it's 5x cubed minus x. Is that even or odd or neither, right? We'll go a little faster through this one. For even, right, I'm checking, is f of negative x equal to f of x? Right? That's what I'm checking. The right-hand side is straightforward because you don't have to do anything, just the original function. The left-hand side is what you get when you plug a negative x in to the original function. Everywhere you see x, replace with negative x. So replace that with negative x, that with negative x. Here, what did we just say negative x cubed was? Negative x cubed, right? So I'm going to rewrite this as negative 5x cubed. So the negative that was in front of the x, I'm just going to pop it out in front of the 5 and make it a negative 5. This is a double negative, which becomes plus. Is that equal to this? Is that equal to this? No. But do you all see that they are off by a sign? Do you see that this is negative, that's positive, this is positive, that's negative? They're off by a sign, which means it's going to be odd. So is it even? No. Is it odd? Yes, it is. Why? Well, when we do this, are we getting this? Yes, this side we already said is this. And over here, we're taking a negative in front of the original function, and we distribute that through, and these two match, right? So it's odd. I'm not going to do this one on the board. Let's just think about it. This one right here. The absolute value of x. The absolute value of x. Even. Would it be even? If you plug in a negative, is it the same as plugging in a positive?
Yeah.
Yes, right? Because if you plug in negative 4, you get the same as plugging in 4, right? Okay.
So because if you know what the graph looks like in your head, you can just do it quickly.
Exactly. If you knew that the absolute value of x, if you knew that this graph looks like a what?
V.
Like a V. If you knew that, then you could see that you have y-axis symmetry, which means it's even. Which is why we did the first part, right? We talked about graphs first, because if you know the graph, it's pretty simple. If not, you have to do it algebraically. Okay, where are we at time-wise? I've got 10 minutes still. Is that right? Feels like this has been a drag class, huh? All right, stick with it. We're behind, okay? We are behind in this class, so I'm trying to go at a pace that I don't lose everyone, but we are behind. So we got to catch up somehow, at some point. All right, here we go. Moving on to a new definition. And this definition involves what's called increasing, decreasing, and constant functions. So there's a definition here, okay? The definition is a little bit confusing. I'm going to try and explain the first definition and what it means for a function to be increasing on an interval. Because when you read it, it's like, what the hell is this talking about? So for a function to increase, if a function f is increasing, on an interval, what do you think when you hear the word increasing? What do you think the function's doing? The y values are getting bigger? So if you look at it from left to right, like you'd read a book, the function's going up. That's what it means for a function to increase. Here's how you say that algebraically. So if f is increasing on an interval, then for x1 less than x2, we have f of x1 must be less than f of x2. What the hell is this saying? All right, well, let me just draw it, because it looks bad, but it's not as bad as it looks. Okay, let's say I pick an x1. That's just some x coordinate, right? And I tell you that it is less than x2, which means it's to the left of x2. Do y'all agree that that condition, that first condition, is being met, right? It says, whenever this happens, then I promise you that f of x1, which represents the y value when you plug x1 in, right? The y value that comes out, that height, that's f of x1, must be what? Smaller than f of x2. So f of x2 is when you plug in x2, you get a value, but it has to be, right? This value needs to be bigger than the one before. Do you all agree that if this happens for any 2 points that we pick, like if I pick any point that is to the left of some other point and we have that happen, do you agree that this graph has to go up? Right? It has to go up. See, from here to here, it has to go up. As long as the point to the left of this point produces a y value that's smaller than that one, then we should have this increasing behavior.
So would one with a vertical asymptote still be an increasing interval?
All the way up to the vertical asymptote, it would be. So because it says here on an interval, right? So the interval that we'd be talking about would be everything up to that vertical asymptote. Okay, decreasing, what's the only difference between this and decreasing?
It would be x1.
This stays the same. When this points to the left of this one, we want this to be what? The opposite, right? We want this first point to be higher than the next one. So we would just flip this inequality over. And that's, if you look at the definition here, that's what it says. Let me erase it here. So that's what these two definitions are saying. If x1 is less than x2, then f of x1 is less than f of x2. That's what increasing means. If x1 is less than x2, then flip the inequality, right? That's decreasing. And then what do you think constant means, to be constant? That means, yeah, not as you go from left to right, the points are always the same. And so it just says here they're equal. And these are the three pictures. There's increasing on the left, decreasing in the middle, constant. Does it make sense? I mean, like visually, increasing, decreasing makes sense, yes? Constant? All right, this will be our last example here. I want us to look at this graph. Maybe that's a little too big. Okay. I could ask you a lot of questions, like the problem we were doing earlier, right? All the list of questions I could ask you, like, for what value of this function, what values of x give you 4, things like that. All those questions that I asked before could be asked, right? But now I'm going to ask you something different. And in 4 minutes. Where is f increasing? So what you want to do is you want to look at your graph, and I like to think of it like you're riding a roller coaster, right? Start at the left, just the way you'd read a book from left to right, and just decreasing as you're going down, increasing as you're going up, right? So first I'm doing what? Going down until I get to the bottom, and then from here, what do? Start going up, right? So from about here, and I'm looking for the x values where they start. From here, right? From here to where? Am I going up? Up, 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 all the way to here, right? Right in here. From here to here. Right? In this little region right here. The function, I'm going to draw an arrow up. The function is increasing there, isn't it? Okay, anywhere else I'm increasing? No. How do I say this to you? Between -4 and? I'm going to use interval notation. I'm going to say from -4 to 0. Now, we run into a little technicality here. If you put -4 to 0, that's okay. That's not wrong. But because of some stuff that happens in calculus, to be safe, always use parentheses on your, when you're talking about increasing and decreasing and constant, just use open intervals. Always use the parentheses because it's not wrong to leave off the endpoint. It's not incorrect.
So you wouldn't do -4, -2 to 0?
No. No, you don't need to say from -4 to -2 and then from 2 on because you are going up here. You're continuing to go up. Like you don't stop going up. Okay? All right, we're almost done. Let's do decreasing. Where is f decreasing? 2 different places, yeah. We're going down, right? In this region, we're going down from here to here. That's from here to here. We're going down. Where else? Up, 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 flat. From here to here, right? So my function f is decreasing here, and my function f is decreasing here. So I'm going to have 2 intervals that represent that answer. And I will put parentheses on them to be safe. Again, it's not wrong to do this. So it's the x values. -6 to where? -4. Be careful, it's not -2, right? That goes with this. So -4 here. And then from 3 to 6. Union 3 to 6. Okay. Last thing, where's f constant?
0 and 3.
That would be right in here. From here to here. Right in here, our f is, how do I do constant? I just do a flat line like that. F is constant between 0 and 3. All right, for your homework, do as much as you can from 3.2. Do everything you can from do everything that's on the schedule for 3.2. We just started 3.3, right?
Oh,
This is 3.3. So for 3.3 homework, I'm looking to see if there's anything you can do here. The only thing on 3.3 homework that I feel safe with you doing right now is 25 and 31. And let me see here.
33.
Yeah, let's just stick with that for now. So 3.2, do all the homework that's on the schedule. 3.3, just look at those. These are looking at a graph, seeing if it's even or odd. Oh, you know what? I take that back. There's a little bit more. Sorry. The 37 through 48. Okay, these are the ones that we did a second ago where you had to algebraically say, are they even or odd? Do as many as you can out of this. That's a lot of problems. This is the one where you have to look, like, is f of x equal to f of negative x equal to f of x? Is that true? If not, check if it's odd. That's all of these. So do all this homework, do as much as you can, do these, and then do as much as you can from this. All right. No quiz next class. No quiz. All right. We will not have a quiz, but that doesn't mean don't do your homework. Have a good rest of your day, everyone. Sorry to put you all in the bad mood to start the class, start the day off. Let me turn this off real quick.